Hello everyone, and welcome to a lesson on the mole. Today we are investigating how a chemist uses Avogadro's number to exchange between the unit known as the mole and the individual representative particles we count. Those particles, of course, being atoms, molecules, or formula units. The tools that I'm going to ask that you have out, you're going to need your mole map, and we're going to be just traveling back and forth in the direction of counting and exchanging to the mole. We know that a chemist can measure matter three different ways: counting, by weighing, or by taking a volume. All three roads always lead back to the central calculation known as the mole. We need a place to start. We'll start in the world of Avogadro's number, counting and converting into the mole, or vice versa. So a simple exchange going back and forth on this particular road. So the mole map may be a helpful tool. We're going to be hitting our calculator. Please be sure you have your calculator out so you can hit the problems with me. And we have our notepad. Our notepad on chemical quantities called the mole, and specifically opened up to page 2, where we have some sample calculations. The sample calculations start where we left off yesterday in terms of our notepad page 2, about halfway down. Pause the video until you're ready, and then start up again when you have your tools out. All right, looks like we're ready. Let's read together our first sample problem in calculating the mole. Let me zoom in on that so we can take a good close look at it. How many moles of magnesium is 1.25 times 10 to the 23rd atoms of magnesium? Our first sample calculation. Now, to give myself plenty of room to set up this problem, I'm going to put on another sheet of paper. You certainly will write down everything I write down, but in a smaller version of it. I just want to make the print large so that everyone has an easier time seeing it. Let's get a handle of what unit we were given and what we want to know. We were given the number of individual atoms of magnesium. 1.25 times 10 to the 23rd atoms of magnesium. This word atoms is a very specific type of representative particle. We're being asked to convert the number of atoms into the mole. If I trace the little road map, leaving the world of atoms and heading directly to the mole, I literally trip over my conversion factor from individual atoms exchanging to the mole. Now, be very careful and write exactly what I have on my paper. Exactly. We always start by writing the number given, 1.25 times 10 to the 23rd times 10 raised to the 23rd power. I don't want to see E, and I don't want to see any other form of scientific notation other than the correct way to write it. 1.25 times 10 to the 23rd is the number given. We must then always write the unit, which is atoms, and the label, which is magnesium. I'm emphasizing every step, every time. Number, unit, label. It would make all of us very sad if we got a correct answer and received no credit at all because we didn't set up the problem right. Number, unit, label, every step, every time in chemistry. The given quantity, 1.25 times 10 to the 23rd atoms of magnesium. Now comes our conversion factor. A conversion factor is two equivalencies set over each other to exchange units. We want atoms to cancel. Atoms must go on the bottom. We want to convert into the mole. The unit we want over the unit we're given cancels units in a conversion factor. Here's what we know: that we have an Avogadro's number, 6.02 times 10 to the 23rd atoms of magnesium, is equivalent to saying 1 mole of magnesium. Number, unit, label, every step, every time. Our conversion factor cancels atoms of magnesium and brings me to moles of magnesium. Now let's talk about the key sequence on our calculator. When we hit scientific notation on our calculator, it's the EE key on my calculator. See where it sits above my comma? That's the times 10 to the. So let me zoom out just a little bit so you can see the keys I'm hitting. I want to hit 1.25 times 10 to the 23rd into my calculator. 1, watch the screen with me, 1.25, and now how I hit times 10. Do not hit times 10 caret key 23 or you will get a wrong answer every time. Scientific notation uses this button, second function comma, to bring up E. That is the times 10 to the button. 1.25 E23 is what's telling the calculator I have a number 1.25 with 23 zeros after it using scientific notation. 1.25 E23. There is no other way to hit that and get a correct answer. Let's get in the habit of good calculator skills for scientific notation right from the start so we don't have to unbreak any bad habits we form. 1.25 E23. Now look at our conversion. Times 1 mole set under Avogadro's number, so 1 over Avogadro. To hit my conversion factor, I could do times 1 divided by Avogadro. Oops, I hit the wrong button there. Let me back up. E23. Now see how in my parentheses, I took my 1.25 times 10 to the 23rd and I'm multiplying it by a ratio of 1 mole set over Avogadro's number. And when I hit that, I find 0.20764. Let's carry 2 decimal places. 0.21 moles of Mg. A number, a unit, and a label. Every step, every time. Now, pause this video until you have indeed mastered how to hit and find the correct number using scientific notation. It might be a brand new thing or it might be old hat. It just depends on how much experience you've had hitting for scientific notation. Let's pause and reflect what we've just done. We were given the number of atoms of magnesium and we divided by Avogadro. Notice he was on the bottom. There's an Avogadro's number of atoms of magnesium. By using our conversion factor with Avogadro on the bottom, we moved from the world of counting into this unit known as the mole. 1.25 E23 divided by Avogadro, and we found 0.21 moles of Mg. As it exactly appears here, you've translated that into your notepad. Best you can, you have to fit that in. Let's go on. Number 2 reads, how many moles is 2.8 times 10 to the 24th atoms of silicon? Given the number of atoms, write this down, 2.80 times 10 to the 24th is my number, my unit is atoms, and the label is silicon. Number, unit, label, every step, every time, or you will not receive credit. Given the number of atoms of a specific element, we want to convert it into moles. It's the same journey. Look at, given the number of atoms, let's exchange to the mole. Just as we had done in the previous problem, heading into the mole is always divide. We know that 1 mole of silicon would contain an Avogadro's number of atoms of silicon. Number, unit, label. Number, unit, label. Number, unit, label. Every step, every time. Now let's hit that on the calculator. Watch my screen and make sure yours is doing the same. 2.80, second function, comma. Do you find your scientific notation? 24. 2.8 times 10 to the 24. Now we could go times 1 over Avogadro, or we could realize that multiplying by 1 is not necessary to type into the calculator. We could simply divide by Avogadro's number, 6.02 times 10 to the 23rd. Does your screen look exactly like mine? You'll know if it reads 4.65. Let's carry 2 decimal places. We'll get in the habit. 4.65 moles of silicon. Number, unit, label. Every step, every time. Let's take a peek at what the third question asks. How many molecules in 0.36 moles of water? Our third question. Look at the journey this time. The unit given is the word mole. That starts us right in the heartland of our mole map. We want to move from the mole out to the individual particles known as molecules. Given a mole, we head out. Again, we use Avogadro's number to exchange, but look what happens to the conversion factor. It's flipped. From the previous 2 examples, we head in, so we divided by Avogadro. Now we're heading out from the mole. Notice what happens? We multiply by Avogadro. Let's set it up to show ourselves. The number, 0.360, the unit is the mole, and by the way, mole is abbreviated MOL. The entire word, MOLE, is abbreviated with 3 letters, MOL. And the label, a number, unit, label, every time, every step. This time, we want moles to cancel, so that unit had better go on the bottom. And notice now, we have a compound. Water is not a single element. It's larger than that. It's a compound. Both compounds happen to be nonmetals, so the category of compound are known as molecules. Number, unit, label, every time. We know that 1 mole of water would contain an Avogadro's number of molecules of water. Moles times Avogadro converts me into the number of individual building blocks of water, molecules. Let's hit it together. Please don't wait for test day to make your calculator your friend. Hit with me. 0.36 times 6.02 times 10 to the 23rd. Your calculator needs to have the E button. 6.02 times 10 to the 23rd. Make sure it looks the same, and you'll know if it's correct, if it matches. Now look at how to read this. 2.1, carry 2 decimals, 2.17, see at the very end, E, that's times 10 to the. 2.17 times 10 raised to the 23rd power. It's 23 zeros after it. Let's record that. 2.17 times 10 raised to the 23rd power. I do not want to see the letter E on your paper. That's the calculator screen, but that's not the correct way to write scientific notation. There's the number, the unit is a molecule, and the label is water. 2.17 times 10 to the 23rd molecules of water is the same as having 0.36 moles of water. Let's try another. Number 4. I'll read it for us. How many moles are equal to 2.41 times 10 to the 24th formula units of sodium chloride? Notice sodium chloride is a compound. It's made of a metal to a nonmetal. Metal to nonmetal are known as ionic compounds. Their building blocks are called formula units. We have a large quantity, 2.41 times 10 raised to the 24th power of these little building blocks of table salt called formula units. How many moles would we have? Well, let's see. Think about the journey. We were given the individual number of particles. We want to head into the mole. what might our conversion look like? The number of formula units needs to cancel. Do you see how Avogadro will go on the bottom? 1 mole of table salt, called sodium chloride, would contain an Avogadro's number of formula units of table salt. We get the formula units of NaCl to cancel, and we've converted to the mole. Hit with me. 2.41, second function comma, brings up your scientific notation E, raised to the 24th power. We divide by Avogadro to cancel our units, 6.02 E23, and hit your equal. Make sure we get a common answer. 4.00. Get in the habit of 2 decimals. 4.00 is the number. The unit is a mole, and the label NaCl. 4 moles of table salt. So far, my friends, we've practiced going back and forth, counting from particles into the mole. We know to divide to head in and multiply to head out, but always the exchange unit is the individual particles, is the world of Avogadro's number. Now let's suppose you want to determine how many atoms are in a mole of a specific compound. Let me give that a little better read. It says, for example, if I have a molecule of carbon dioxide, this is a compound built of nonmetals, so it's called a molecule. Inside this particle known as a molecule, I see 3 individual atoms. This one molecule is built of a single carbon and 2 oxygens. 1 carbon and 2 oxygens gives me a total of 3 atoms. Let's take a peek at how that would affect the math question. How many atoms are in 2.12 moles of propane? Now I'm going to stress something. I'm being asked to count atoms, but I'm given something larger. This is a compound made of nonmetals. This is a molecule. What I call this is a vocab mismatch. And what I mean is we're being asked to calculate something smaller, an atom, than the compound they gave me. And all that tells me in my head, oh, this is going to be a 2-step conversion. A vocab mismatch, when I hear that, is a 2-step conversion. Let me model one. We're given the number of moles, so we're starting the journey in the center of the mole map. But when we move from moles to the individual particles, the particle we were given was a molecule, something larger than an individual atom. Let's take a look. The number, 2.12. The unit is a mole, and the label is propane, C3H8. Number, unit, label. In our first conversion factor, we want the moles to cancel. It needs to go on the bottom. We know that 1 mole of propane contains an Avogadro's number of, what are these again? What is that? It's a molecule of propane. Match the vocab here. So important in this step. You must match the vocab to the particle given. This is where I'm saying, if I were given molecules and asked here to count just the molecules, I'd be done. But it didn't. It asked me to count something smaller than the particle that was given. Atoms are the building block of molecules. Seeing that vocab mismatch lets me know there's one more step. I have a molecule here. It needs to go on the bottom so that the unit cancels. Peek inside this one molecule of propane, and how many individual atoms do you see? Well, there's 3 carbons plus 8 hydrogens for a total of 11 atoms composing this single molecule. Number, unit, label. There are 11 atoms of carbon and hydrogen in every molecule of propane. The second step, I had to match my vocabulary to the particle given. The particle of propane is correctly labeled molecules. In that molecule, it is built of 11 atoms, who are carbons and hydrogens. Now let's hit for our answer. 2.12 moles times Avogadro brings me to the number of molecules, times 11 brings me to the individual number of atoms. There are 1.40, get in the habit of 2 decimals. Look at the very end of your screen, see it? Times 10 to the 25th power. The unit of atoms, and the label is carbon and hydrogen atoms. Number, unit, label, every step, every time. 1.40 times 10 to the 25th power, that's a whole lot of atoms. Asked to count something smaller than the compound given. Atoms build molecules, 2 steps. Let's read number 2 and see how that is very similar. How many atoms are in 1.14 moles of sulfur trioxide? Sulfur trioxide is larger than what we're being asked to count. See, sulfur trioxide is a molecule. Hear those prefixes? Molecules are built of atoms. It's a vocab mismatch. That lets me know it's a 2-step. They gave me a compound and asked me to count the atoms. So let's start just as we did in the previous problem. Number, unit, label, 1.14 moles of sulfur trioxide. In my second, well, it's my first conversion, but the second thing I'll write, I want moles to cancel. Now, we have to correctly match the vocabulary. The correct vocabulary word for what we're counting is 6.02 times 10 to the 23rd molecules of SO3. You must match the vocabulary in that particular conversion. It would be incorrect to put atoms of SO3. It would be incorrect to call these ions. These are nonmetals covalently bonded, correctly labeled molecules. And now I can convert by counting the individual atoms contained in this molecule. How many atoms do you see in a molecule of sulfur trioxide? I see 4. There's an S and 3 O's for a total of 4 atoms. 4 atoms of S and O is my number, label, unit, every step, every time. Let's hit for a common answer. 1.14 moles of SO3 times 6.02 times 10 to the 23rd times 4. Does your screen match mine? 2.75 times 10 to the 24th atoms of sulfur and oxygen. Number, label, unit, every step, every time. Let's try number 3. How many moles are in 4.65 times 10 to the 24th molecules of nitrogen dioxide? Let's consider what we're being asked. They gave me a molecule of nitrogen dioxide. This, by the way, is a vocab match. Now what I'm saying, the number of molecules of nitrogen dioxide, it'll be a while, is a molecule. So we have a vocab match. It's going to be a one-step problem. Let's start by writing our number label unit. 4.65 times 10 to the 24th molecules of NO2, nitrogen dioxide. We're going to set up a conversion using Avogadro's number. 1 mole of NO2 is the same as saying 6.02 times 10 to the 23rd molecules of NO2. A one-step conversion because the vocabulary matched. Molecules cancels directly. We've just traveled from a molecule directly into the mole with the one-step conversion. Let's hit that together and get a common answer. Don't cheat yourself. Hit this on your calculator. 4.65 times 10 to the is the E key to the 24th power. Divide by Avogadro. And I found 7.72 moles of nitrogen dioxide. One-step problem when the vocabulary matches. A two-step problem when the vocabulary does not. Let's consider one more together to finish this notepad page. How many atoms of carbon are in 2 moles of sucrose sugar? Is this a vocabulary match or mismatch? We're given a compound. This compound is built of all nonmetals. This compound would be known as a molecule, and molecules are built of something smaller called atoms. This indeed will be a two-step conversion, a vocabulary mismatch. Let's set it up by writing our number, 2.0. The unit is a mole, and the label, sucrose sugar, C12H22O11. Number unit label. We know that there is an Avogadro's number, 6.02 times 10 to the 23rd, and now watch, you must match the vocabulary to what the compound was. It is a molecule, since all of these combined are nonmetals. We have a mole of sugar when we have an Avogadro's number of molecules. We must match the vocabulary in this step. We were counting molecules. But remember, we had to go one step further. How many individual carbons do you see? Well, in every one molecule of our table sugar called sucrose, not the total number of atoms as in the previous examples, but just the number of carbons. And you count 12 just like I do. There's 12 carbon atoms. Number label unit every step. Let's hit for a common answer. Let's hit together. 2 moles of sucrose times Avogadro 6.02 E23 times 12, the number of carbon atoms. And I bet you found 1.44 times 10 to the 25th. Look all the way to the end. Don't forget to grab the times 10 of the part. Correctly labeled as atoms of carbon. Two-step conversions when we have vocabulary mismatch. One-step conversion when they do indeed match. What I'd like you to do now, come find me for your homework assignment, and I'll be passing tests back here soon. So when you've completed through section 2, you're done with this, or through page 2, you're done with our video lesson.